In this video, we will start with inference for trend stationary processes. And let us start by rewriting the model equation of the deterministic trend model slightly over here, namely in matrix notation. Remember, in the deterministic trend model, we regress yt on a constant alpha, a time trend, and we start with IID errors. Now I collect all regressors, so the constant and the time trend in one vector xt. And the parameter vector includes alpha and delta, where I call the parameter vector beta. Then I can compactly write down the model like this. And as said before, I will work with IID errors for now. And also assume that the errors are bounded. Now, why is this popping up? Well, you will see that you need this boundedness here in the central limit theorem that you will make use of in your tutorials. Now, if we want to derive the limiting distribution, we should start with the definition of the least squares estimator, which is just simply equal to x prime x inverse times x prime y. Then we've also seen that we should plug in the DGP indicated here in blue, which is nothing more than yt being equal to xt beta plus the IID error. Now for the first term, x prime x inverse times x prime x will just cancel out, give the identity such that only beta is left. And on the next line, I've immediately brought beta here to the left-hand side, such that you're only left with the second term over here. You should definitely be able to routinely perform these first steps as of now. Now, how would we continue for stationary time series? Well, we would introduce the appropriate scaling, which is the asymptotic rate of convergence. So by which we blow up this difference between the estimator and the true parameter value. Now, until now, this was always root t. And we would place a factor 1 over t on this term here for the law of large numbers. And here we would have our scaled average with a factor 1 over root t for the central limit theorem. And our next steps would then be to show that this guy converges in probability to, let's say, q by the weak law of large numbers. And we would use the central limit theorem to derive the limiting distribution of this guy. And then in order to derive the asymptotic distribution of our estimator, we would combine both pieces through, for instance, the continuous mapping theorem. Now let's have a look at how we would scale here in this term. And let us start with the cross product of the x's popping up over here. So in the first term, we start with the cross product of the x's. Now first, since x is a vector consisting of two elements, this cross product would give us a 2 by 2 matrix. And let us write out what xt is, namely the vector of our constants. So we have a 1 over here, and the time trend. And if we carry out this matrix multiplication, we would be getting a sums of 1s over here as the first entry. And the bottom left and top right, we have a sum of t's. And for the bottom right entry, we have a sum of t squared. Now in the first tutorial, you have seen these sums in t. Of course, the first entry is just equal to the total number of observations or the time series length, capital T. In the first tutorial, we've also seen that the expressions of the sums of T simplify to these expressions over here. Please verify that by looking back at your tutorial assignment. We also derived the leading terms of these two sums, the sums of t and the sum of t squared. And for the first term, the leading term is just t. For the sum of the t's, the leading term is t squared. And for the sum of t squared, the leading term is t to the power 3. So we see that the entries in our matrix actually diverge at different powers of t. Now, what would happen if we would just work with the scaling from the IID world or the stationary world? Well, then we would divide by 1 over t, and our sum would still diverge since we have larger powers of t popping up over here. So this is already in sharp contrast with the stationary case, where everything worked nicely with the factor 1 over t on this term. So the question then is, how do we get the matrix to converge? Now, as a first instinct, you might have to introduce scaling 1 over t cubed, so t to the power 3, since that was our highest order leading term. Now note, however, that this guy over here then converges in probability to this matrix, where we just obtained the probability limits of the elements one by one. So we indeed converge, which is good, as you might think, but this is actually still problematic since we cannot invert this matrix while we actually need its inverse, as we need the inverse of the cross product matrix x prime x in the least squares formula. So this will also not work. So we actually need a different approach to calculate the asymptotic distribution. Now, what is this different approach? Well, we will determine the leading term. We will determine the leading term of each entry separately. Remember, the first entry over here had t as leading term. The sum in t had t squared as leading term. And the last entry had t to the power 3 or t cubed as leading term. What we will then do is introduce a diagonal scaling matrix denoted over here by epsilon t. We will pre and post multiply our cross product sum with the inverse of this scaling matrix, such that each entry gets its appropriate scaling. So for the first entry, we need scaling by 1 over t. So if we set the first entry equal to root t, we indeed get scaling by 1 over t, since we pre and post multiply by the inverse of this scaling matrix. For the bottom right entry, we need scaling by t cubed. And if we introduce here the second element on the diagonal t to the power 3 over 2, this indeed gives us combined a factor 1 over t to the power 3. Now for the off-diagonal elements, we would then get the combination of these two powers, which is the desired scaling immediately, t to the power 2. And then we can derive the convergent matrix after having introduced this scaling by just computing the probability limit for each entry separately. The first entry, of course, converges to 1. And in the tutorial, you have seen already that these sums go to a half, and this latter one here goes to 1 over 3. Now, with this appropriate scaling matrix given by the matrix epsilon, we are now ready to blow up the difference between our estimator and the true population parameters with these appropriate scaling factors given on the diagonal of the epsilon matrix over here. So that was root t and t to the power 3/2. Now, since I introduced the scaling on the left-hand side, I must also introduce it to the right-hand side, which I do over here. Now, on the next line, I introduce the product of the scaling matrix and its inverse here in the middle, which I can do since this gives me just the identity matrix. And then I just pull in these scaling matrices inside of the inverse. This guy goes here, this guy goes here, and that guy goes over there. And so, of course, I can insert them into this inverse if I also invert them. And so note that this guy here just simply goes to the second term. And then I'm ready to derive the limiting distribution of my estimator. I copy this on the next slide. We start by deriving the limiting distribution of this first term, which we actually already did on the previous slides. And for the last term, we would need to rely on the central limit theorem to show that zt, which is this vector over here, converges in distribution. Now, the first element is easy since this is scaled average of IID errors, and we can simply rely on the central limit theorem for IID sequences. In the tutorial, you will dive further into the limiting distribution of zt for the deterministic trend model. Now, how can we make use of these results in practice? Well, you can use it, for instance, for hypothesis testing. Let's look at a very easy example on this slide over here. Let's say that, for instance, we collect temperature data from some location in the Netherlands, and let YT denote our temperature series. And you might be interested in estimating this deterministic trend model. Now, it's a very simplistic case, but we might be interested in testing the null that delta is larger than 1. Some of you might actually have seen this example popping up in mathematical statistics during your bachelor's. Now, as you can see in Hamilton, it actually turns out that the limiting distribution of the test statistic follows a standard normal distribution. So despite the fact that we have seen that the estimators for alpha and delta in this model have different asymptotic rates of convergence. Remember, we had to blow up this difference here between estimator and true population parameter by different powers of t. So despite that fact, their standard errors have offsetting asymptotic behavior such that the test statistic still follows a standard normal. Now, that is nice, of course, because then we can rely on our classical inference toolkit. Now, we've seen in this video how to conduct inference in the deterministic trend model. In the next video, we will look into the random walk model.